This is Daniel Coosbury, and in this lecture we are delving into Chapter 10, which is all geometry and stuff. So this section's got a lot of different definitions and things, most of which you should have seen at some point. And it kind of throws all those definitions on the front end. So I'm just going to kind of talk about a few things really briefly, and then we're going to do some problems. So this section's about points, lines, planes, and angles, and these terms are related in that you kind of start everywhere. You kind of start building up everything in geometry with points. So all a point is just some little dot, and I give it a name, usually a capital letter A, and I use that point as kind of a point of reference, and I can connect points and make different things. So if you connect 2 points, you've got a line, assuming that that line goes through 2 points, and this is how we would name it. We'd name it line AB. And specifically speaking, a line connects 2 points, and it theoretically goes on forever and ever in each direction. So we'll denote that with a little arrows on each side. That just means that this line, in theory, just goes left and right forever and ever and ever. So we can distinguish that from some other kinds of lines. So here's another line AB, and you can write it line AB, or you can write it with this little arrow over the top. It's a double arrow because it's denoting that the line goes left and right forever and ever. Or you could also call it line BA if you wanted to. It doesn't really matter because these arrows go off either way. You could switch the order, which means you're going from B to A, and it's the exact same thing. We also have a concept of a half line, in which, notice there's a little open circle here. If we call this the half line AB, you've got a little open circle, which means the line starts right past this A. It doesn't actually include the point A, but it almost does. And it goes through point B, and it goes to the right forever and ever. So there's some sort of concept of direction now. You can notice the order matters here. We can't call this line half line BA because that would suggest it was going the other way, and it's not. So when you got arrows going off both sides, the order doesn't really matter in how you name it. But when the arrow is going off of one side, the order makes a difference, and you've got to name it the right way. We also have the concept of array, which I think you've probably seen before. An array does include those 2 points, and it's a line that goes off just in one direction. So array AB, notice we denote it with the arrow going the appropriate way. Starts at A, it goes through B, and it keeps going into infinity. It only goes one direction. So that's an A. Note the difference between a half line and array is that the half line doesn't include that point. The array does. And the last thing we have is line segment AB, which is a segment that connects 2 points, and it doesn't go off either direction, which just means that we can write it as line segment AB. Note there's no arrows here. Or we could call it BA because there's no arrows, the direction doesn't matter. Whereas here, there are 2 arrows, the direction doesn't matter either, so we can switch it. But when the direction makes a difference, we can only pick one of those naming conventions. We can't call it the other thing. We couldn't call these 2 in the middle BA because it would misrepresent what's going on. So those are different kinds of lines. And then you have the concept of a plane, which you get from putting 2 lines together. So if I take a line, maybe we'll put some points here. This is going to be really hard to draw. And I'll take another line here. Then you can imagine these 2 lines together forming some kind of a plane, some kind of a rectangular space. It's 2-dimensional now. And you can talk about points being on that plane. With planes, I like to just imagine like this was a sheet of paper. It's 2-dimensional. You can kind of see the directions of the sheet of paper, but there's nothing that kind of goes through the sheet of paper like that. That wouldn't be part of the plane. The plane would only be those 2 dimensions that it represent. And so you can make a plane with 2 lines. The most common plane we use is the XY coordinate plane. That's what we call it. That should be a Y. The XY coordinate plane. You have an x-axis and a y-axis, and that makes your plane. It's 2-dimensional, not 3-dimensional. So anyway, that's what that means. We don't see a lot of plane stuff in this section, but there's the definition. And then we have the concept of an angle, which an angle is formed when 2 lines or 2 segments or 2 rays intersect, and we want to talk about the measure of this angle that's formed by the 2 lines or segments or rays or something. So here we have 2 rays. They intersect at point B, and there's an angle right here. We'll call it angle 1. And notice there's a few different ways to name the angles. We can call it angle 1 if we write a little 1 in there. We can also call it angle B if it's the only angle with the vertex B. So sometimes there's more angles coming out of B, so we probably could call it angle B, but since this is the only one with the vertex B, then we can call it angle B. And then probably the easiest way, I think, to specify which angle you're talking about is by using the 3 points that form the angle. So ABC, starting here, ABC, that would be talking about this angle, or CBA, CBA would also be talking about this angle. Note the vertex is in the middle, which is how you know for sure this is the angle we're talking about. But again, if the vertex only forms one angle, then you could also just call it angle B if you wanted to. Okay, that's all the definitions. And now let's look at some examples. So we're interested in a clock hand that moves from 12 o'clock to 4 o'clock. That means that this little short hand is now going to be pointed towards the 4, and the long hand is still going to be pointed up. And now we have a little angle that's formed from the 12 to the 4. Now, one thing we need to know to do this kind of problem is to note that the distance around a circle, if we were to take this vertex and kind of move it all around, the total distance, the angular distance around the circle is 360 degrees. So that's the total. If we take this hour hand and we spin it all the way around, it'd be representing 360 degrees, which means anything less than that is going to be kind of a piece of that 360 degrees. So for example, we have the concept of a right angle, which is formed by 90 degrees. And so you can also note that if we have two of those, we end up with a straight angle, which is 180 degrees, and then we can keep going. And if we keep going, you'll see that should add up to 360 degrees. We also have some more terms down here. There's an acute angle, which is less than 90, and an obtuse angle that's more than 90. We typically don't have a name for anything bigger than a straight angle, like something that would go down here. We'd probably just call it an obtuse angle on the other side. But notice the total distance around the circle is 360. So if we wanted to find this angle right here, we're going to set up a proportion where we know that this angle is going to be a percentage or proportion of the total 360. And so part of our equation is going to be this. We want to know what part of the 360 degrees is made up by this angle. And we'll use the numbers on this clock to kind of fill in the rest of it. We know that the fraction formed, or the piece of this clock that's formed by the 12 o'clock, the 4 o'clock, we know there's 12 total hours, and we only want to capture 4 of those hours. They're evenly spaced, so we can set up that proportion as 4 out of 12. This is just a fraction of the total clock. This is 4 hours out of the total 12 hours, and we want to know what percentage of the 360 degrees. So now we have a proportion, and we can cross multiply and divide with this, and we get 12x is equal to 4 times 360, which is 1,440. And then we do the division, divide that by 12, and you got x is equal to 120 degrees. And which, if we think about it, at least look at our picture, if that's a right angle, that's 90 degrees. This is bigger than a right angle. 120 is bigger than a right angle, but it's not as big as a straight angle, which would be down here. So that's a reasonable answer, and we can kind of think we probably did this one right. Okay, among the many terms in this section are complementary angles. Complementary angles is this idea that if you have a right angle, we denote it with this little box here in the angle. Complementary angles would be two angles that form that right angle. So there's one angle, there's another angle, and we know because they kind of split this right angle into two pieces that these two angles have to add up to be 90 degrees. So that's what complementary angles means. So here's an example of pretty much what I just drew. We have a right angle here. It's kind of split into two pieces by this ray here, and we know that this one this one angle is measured 62 degrees, and we don't know this one. But we do know they're complementary angles. So I'm gonna call this x, and we're gonna find x by just simply noting their complementary angles. If you add up this measure and this measure, you should get 90 degrees, which means if you subtract 62 from 90, you get your angle measure. X is equal to 28 degrees. So it's a nice, useful tool, and it's going to be, we're going to see it's going to be used for more complicated problems here in the future. But first, let's look at supplementary angles too. I didn't write that on here. So this is going to be supplementary angles. which similar to complementary angles, we know that if we start with a straight line, that straight line represents 180 degrees. So if we split that straight line into two pieces with a ray, then those two angles that form that straight line should add up. The measure should add up to equal 180 degrees. So this example says that angle DBC is 63 degrees. So I'm just going to write that in here. And we know the total angle measure is 180 degrees. So what this term means, supplementary angles, are these two red angles that add up to equal 180 degrees. So we'll do this problem kind of like we did the last one. If I don't know what DBA is, so I'm going to add x plus 63 is equal to 180. X and 63, these two are the measures of supplementary angles. So if I do subtraction, then I get x is equal to 117 degrees, which is reasonable. It's some kind of obtuse angle. We can see it. It's pretty clear. So you got your ideas of complementary angles, which add up to 90, and supplementary angles that add up to 180. We also have the concept of vertical angles. There's so many terms in this section where vertical angles are angles that are formed when two lines intersect. They just cross like this. And the vertical angles would refer to these opposite angles here. So the one that's measured 68 and the one that's called 1 are vertical angles because they're kind of on opposite sides of that intersection. So the nice thing about vertical angles is they have the same measure. Their measures are equal. That's kind of nice. And you can kind of see in the picture they look equal. So it's just a fact that when you have two lines and they intersect, the opposite angles, which we'll call vertical angles, have the same angle measure, which means we can say the measure of angle 1 is equal to 68 degrees. We don't have to do any sort of math. We just have to know that those are vertical angles and the vertical angles have the same measure. So that's that. And then we want to find the rest of these. And so what I would suggest is delve back into those last few examples and see if there's any sort of ideas from those we can use. And then you might notice that we've got supplementary angles here. We've got a straight line, we've got a ray that splits it in half, not half, but into two pieces. And then we want to know what angle 2 is, for example. So we can say that x, let's call that x, we'll call it measure of angle 2. So the measure of angle 2 plus 68 is equal to 180. Which means if we subtract 68 from 180, we get that the measure of angle 2 is equal to 112. So we can write that in there. So we just use supplementary angles. We use vertical angles. And then we want to find the measure of angle 3. Well, here's a nice thing. Angle 2 and angle 3 are also vertical angles. So that's pretty nice. In other words, we don't have to do any more work. If our measure of angle 2 is right, then the measure of angle 3 is also 112 degrees. And you can also find that using supplementary angles, and you should have gotten 112 degrees using that. But this is kind of a nice little property here. So with all these tools, we can start looking at bigger and bigger problems, and we'd have to use as many tools as we need to solve these problems. But we're getting close to being able to tackle something kind of big and messy. So speaking of big and messy, here is what we're going to call parallel lines cut by a transversal. So there's 3 lines in here. The parallel lines are going to be labeled, or you're going to be told that they're parallel, but parallel lines just mean they don't intersect. So in the drawing, we're going to see they look like they're going the exact same direction. They don't ever cross. If you imagine these going off forever, they're never going to cross. But we're probably going to be told in the problems they're parallel because it's sometimes hard to see with the naked eye. And then the transversal is a line that just cuts through 2 parallel lines. So we call it parallel lines intersected by a transversal. This line right here would be the transversal. These are the parallel lines. And then from that we have a concept of alternate interior angles. Well, here, let me kind of show you what we have first. We have parallel line, they're cut by a transversal, and we have 1, 2, 3, 4, 5, 6, 7, 8 angles. There's 8 angles now. So that's a little bit intimidating. But we have a few other ideas here that are going to help us find these angle measures. The first is the alternate interior angles. If you look at the parallel lines, the transversal, we have what we're going to call an interior angle here and an interior angle here. They're kind of on the inside of this figure shape, whatever you want to call it. And so one nice thing about alternate interior angles is they have the same measure. That means that the measure of angle 2 is equal to the measure of angle 8. And you can kind of see in the picture it looks like that, and it just so happens to be geometrically true. So we can write that this is 35 degrees, which is pretty nice. All right, I'm going to use a different color now to label other things. We also have this idea of alternate exterior angles, which instead of these interior ones, would now refer to these exterior ones. And those have the same measure, which is kind of nice. So if we know the angle of measure 7, we can find the angle of measure 3, and we don't actually know that off the top of our heads, but we know that we have a straight line here. It's cut into 2 pieces, so we can use supplementary angles to find the measure of angle 7. So we'll just do subtraction, and we get 145 degrees there. So that's going to be 145. That's going to be 145. In other words, if you can find angle 3 or angle 7, you have the measure of the other one. They're exactly the same, which is really nice. And then, let's see. I'll tell you this last one in a second. We actually have enough pieces now to finish this off, because we have vertical angles down here and we have vertical angles over here. In other words, angle 6 is 145. Angle 4 is 145, and we have angle 2 is 30, or angle 5 is 35, and angle 1 is also 35. So one of the nice things that parallel lines and a transversal gives us is we have alternate interior angles, alternate exterior angles, and just with one of those, we can actually solve all these, because we got vertical angles, we got alternate interior angles, and so we can use all those pieces just to find these 8 angles. And all we started with was the measure of 1. They gave us the measure of 1. We use that to find the rest of them. Now, the only thing on this thing I haven't talked about is corresponding angles. And I'll just kind of highlight those. When you have parallel lines cut by a transversal, you have angles that are basically like in the same spot. So since these are parallel, this shape right here, these 4 angles look exactly like these 4 angles. If you just kind of move your eye from here to here, the angles look the same. And so we'll say that like corresponding angles are the angles that are in the same spot. So like angle 3 and angle 6 are corresponding angles. They have the same measure. In the same way, angle 1 and angle 2 are corresponding angles, and they have the same measure. Angle 7 and angle 4 are corresponding, and angle 8 and angle 5 are corresponding. And so if you just use that property also, you should be able to just figure that out. So if we started with, I'm going to do something dangerous. Let me just clear this up. And if we started with angle 35, or angle 8 that's measured 35, and all we used was corresponding angles, that would lead us from here to angle 5 and say that's also 35 degrees. And from that, we'll use vertical angles and supplemental angles to figure the rest of these out. So we could have used any one of these 3 things to do it. I'm going to take back what I did now. But the nice thing is these big messy problems, if we know these are parallel, we know we have a transversal, then we have all these things that we can use, and we really only need to use 1 or 2 of them to do it. So that was a lot of terms, a lot of things, but at the end of the day, we now have a lot of building blocks to solve, find the angle measures of big messy things like this.